Now, sir, you can start, sir.
Can I
Uh,
start now?
yeah,
So this
yes.
one is
Thank you,
for
sir.
how much time? Like how much time I have for this one?
Sir, 1 hour or 1 hour, 15 minutes, 20 minutes, whatever you like, will can end.
So, and that's all for the day, correct?
Yeah, sir. After that, that's all for the day, sir.
Okay, okay.
Yeah.
All
Okay.
right.
Thank you, sir.
So again, yeah, I hope everyone joined, but let me start. All right. Welcome back again. So now I'm going to talk about like a non-traditional stabilizer, like a geopolymer. So these are the slides. Some of the slides I just took presented in IGC, uh, recent last IGC. Anyone if someone was present there, so they'll be listening to the same thing. But I'm just going to talk about a little bit of stabilization. Geopolymer stabilized highly subgrade using industrial byproduct. So talk about the background and then some problem, and then what are the experiment we did, and some statistical results and the sustainability assessment. And also, it is not there in sustainability assessment for maybe the next early, but I'm going to explain that and then and the conclusions. So as I mentioned, all these methods you already explained, densification, consolidation. So this is the chemical modification in the geopolymer salt stabilization we're going to talk. And so here now, why are you using geopolymers? What is the problem first? So people most of the time you use uh, the road condition is not very good. Uh, Even people are using cement, so that produces you know million tons of CO2. And then also here in this particular experiment, we did a lime sludge that is an uh, industrial byproduct from the water treatment plant. We use GGBS from the steel industry. We use coal ash from the thermal power plant. Okay. So here, so basically these are the experimental plants. So we used EPK clay. So this is a commercially available clay. And then you use fly ash, lime sludge, and GGBS. And then you use different combinations. And so because this fly ash was class F, so we use that fly ash with lime ash and fly ash with GGBS just to make it more pozzolanic. And then we did different geotechnical properties, physical properties, and then we do the structural analysis, and also we did sustainability analysis. So now the thing is for geopolymer, I'm going to talk about that. So geopolymer mostly when you add that different material, and then pozzolanic material, and then also the sodium hydroxide and sodium silicate. These are the two things you need to add. Basically, and we need to increase the temperature. Basically, the reaction should be the reaction takes place at high temperature. So that is the little bit of practical problem for geopolymer. But here we just check with what is happening when you use like a normal temperature, ordinary temperature that is 23 degree, and compared to the 70 degree, generally use 65 to 70 degree Celsius for this geopolymer. Okay. And then also we check like which one is better, whether fly ash lime size is better or fly ash GGBS is better. So both are waste material. So the idea is basically use that waste material instead of using cement or lime, all this waste material to stabilize the soil. So geopolymer, as I mentioned, geopolymer inorganic molecule synthesized by an activated polycondensation reactions. So basically, you see the silica, alumina, the silica, oxygen, alumina. These are the physical structures. Basically, the Zhang et al. 2010, the chemical structures of geopolymer is Mn, silica, SiO2, Z, Al2, AlO2, and then N. So M is the alkali cation, such as potassium. It can be potassium, it can be sodium. That balances the negative charges for the aluminium. And N is the degree of polycondensation. It can change. We can change the alkali to silicon alumina molar ratio ranging from 1 to 15. Okay. So most of the time, so that as I mentioned, so the silica and alumina, you can change, and also you need to use that the alkali, mostly either sodium hydroxide or potassium hydroxide and the sodium silicate. So first thing is the first phase is dissolution of amorphous silicate material. So silica, so soil is clay is having mostly the silica and alumina iron, right? So silica and alumina is dissolved by this sodium oxide, and sodium silicate. And then the reaction takes place, and then the Foley condensation of the dissolved species takes place. And then this and the geopolymer form. So over here, you see the step one, chemical attack, then dissolution takes place, gelation takes place, polymerization takes place, and the growth, and then basically the geopolymer is formed. So people already studied the studies for geopolymer soil stabilizations. Over here, you can see the UCS strength, how the UCS strength grain after 28 days. Over here is 110 to 124 ESI. And this is the reaction, basically the clay particles and the silt particle find and the precursor when we add it. So what is the reaction? So basically all the voids over here, this was voids, so all the voids with the reacted product or synthesis geopolymer. So this is some of the another results also the people have done. The compressive strength 7-day, 28 days. So 28 strength is much more. Some cases, the 7-day curing is much more than 28 days for the different combinations. So as I mentioned, so you need to do different tests and then find out which one is that optimum percentage. So here for the current study, basically one of my PhD students, he did. So the class A fly ash, we use GGBS and lime sludge. And then we use alkali activators, sodium hydroxide and sodium silicate, not the potassium hydroxide, sodium hydroxide, sodium silicate. And then we did the experiment for normal temperature, that is room temperature around 23 degrees Celsius, and then elevated temperature basically for 75 degrees. So and then also we did the sustainability assessment. So again, the life cycle cost assessment. So we use that embodied energy, we use the environmental impact, we use the life cycle costing, all these things, and then 3 index find out that that sustainability index, resource consumption index, environmental impact index, and then socioeconomic impact index. Again, we used the data from the standard data we use, but there are different softwares. You can use CIMA Pro and other to calculate all the sustainability index. So here, what we did mostly, we mixed with EPK clay with different stabilizer, as I mentioned, lime sludge, GGBS, and fly ash, and we did the basic test, specific gravity test, particle size, liquid limit, XRF. And then also we did that UCS test, we did LCA test, and then we did FTIR and X-ray diffraction, all these different tests to check what is forming inside that after the stabilization. Okay. So these are the different combination of tests we used. And over here, so all samples are cured at 7 and 28 days, and amount of binder percentage is basically calculated based on the dry weight of the sample. And then also we used the control test without anything, that is 100% EPK clay. And then we used EPK clay plus 5% fly ash, 5% lime sludge, and GP is basically the geopolymer. So we added that sodium hydroxide and sodium silicate solution. So, and then that 5% fly ash, 5% lime sludge. Second one, M3 is basically EPK clay plus 10% lime sludge, 10% fly ash, and geopolymer. Then we use like a 10, 15, 20, same thing for 10, 15, 20 for lime sludge. And we use that only, the lime sludge percentage you changed, So basically we used the only lime sludge and geopolymer. We used fly ash plus lime sludge with geopolymers, and we used fly ash plus geopolymer, GGBS and geopolymer, also fly ash plus geopolymer. So different combination, we check which one is more suitable. Okay. So, and then I'm not going to go in detail the procedure. So basically the sodium hydroxide, this is very important. So in this case, we use like a sodium hydroxide and sodium silicate ratio is 1.5. And then the ratio of this, the total weight to the sodium ratio of the ash to alkaline liquid, which is total weight of the sodium silicate solution and the sodium hydroxide solution maintained 0.55. Just for example, like this is like a water to cement ratio in concrete. So we maintain that 0.55 and the compaction is done in 3 layers. And then for ECS strain, these are the rate of strain 0.05 inch per minute. And then we did test for 23 degrees Celsius. There's ambient conditions, and we use that 70 degrees Celsius. And test has been done for the 7 days and 28 days. And the moisture content of the cross samples recorded after 28 hours. 24 hours. This is the particle size division graph for EPK clay, lime sludge, fly ash, and GGBS. You see the GGBS is more coarser, and then there's the lime sludge, and then fly ash is more uniform, and then EPK clay. These are the properties of the EPK clay. The specific gravity is 2.61. Liquid limit is 72.7440. Plasticity index is plastic limit. Plasticity is 34.9. Maximum dye density is 1109 kg per meter cube. And then optimum moisture content is 33%. It's quite high. So as per USCS classification, this is treated as high plastic silt. So properties of EPK clay. So mostly you see here, mostly the silica is a major component. Calcium is 0.18%. So EPK clay is basically just 1:1 clay. So you know that the silica, alumina, and so silica tetrahedra, alumina octahedra, how they are arranged. So 1:1 or 2:1. These are the chemical compositions of the fly ash, lime sludge, and GGBS. So you see the first column is the fly ash. So here calcium is 3.8%, is very less. So this is class F. And then if we add these first three, silica, alumina, iron, it is more than 70. So that is class F. Lime sludge over here, it is a byproduct from the water treatment plant. The calcium carbonate, calcium oxide content is 51%. That is good. And then GGBS is also 42%, the calcium. So calcium is the one we needed, for binding. So here, this is the test results for stress strain behavior of 7 days when we combine with fly ash and lime sludge, but it is in MPa. For EPK clay is lower one, and you see here the strength is going up with different percentage of fly ash and lime sludge combinations. And so this is the figure B is the same test, same combinations, but with high temperature. This is 23 degrees Celsius. This is 70 degrees Celsius. So geopolymer is basically the reaction is not going to occur unless you elevate the temperature. So the problem is in real life and practical applications, how we're going to increase the temperature at the site. So that's why we tried both method and see what is happening. So how much is the strength increase with temperature increase, and then how much is the ambient situation. So this is for EPK clay with fly ash and lime sludge. This is the one. This results is basically with fly ash and lime sludge combined. Okay, fly ash and lime sludge combined at the same train. After 28 days, the elevated temperature shows more strain compared to the normal temperature. But this is also quite high strain. That you see a 5% fly ash and lime sludge is 4 MPa is quite a strength. Then here in this case, this is we tried with temperature a little bit increase. Instead of ambient temperature, we increase 35 degrees Celsius and see how much is the strength gain. And then we see that, at 70 degree, the strength was at 28 days almost 6 MPa. So here, 28 days, the strength is around 4 MPa. It's not that bad. But compared to the ambient one, it's a little bit increased compared to the ambient one. Okay. And then this is the results for 28 days strength, again, fly ash with GGBS. Earlier when the fly ash with lime sludge, now fly ash with GGBS. So again, elevated temperature shows higher strength compared to the ambient temperature. This is overall, you can see here the effect of fly ash and lime sludge, what is happening in the 7 days and 14 days. So most of the time, the 7 day strength is lower and 28 days is higher. Everywhere you can see that. But some cases fly ash and lime sludge combinations, at elevated temperature, 7 day curing is more than this 28 day curing. Okay. So this is again from the Stetson graph. We calculated the modulus, plastic modulus, and we calculated that for different temperatures and different combinations. So most of the cases, modulus rigidity in the slope of that Stetson graph. So it's more means it can take more load, more stiffer, and then the 70 degrees Celsius in the higher temperature, again, it shows higher E value, modulus of elasticity. And then for the same thing for GGBS and fly ash content and the 7 days curing and 28 days curing, what is happening for the UCS test results. So most of the time it is like is increasing from the original one to 5, 10, 15 is almost the same. It's not much change. So here 5% even giving more results than 15, 20, and 10, 15, and 20. So again, as I mentioned earlier, so we need to really do that test and then find out for which one is optimum for any soil separations study. So this is again the modulus of plasticity material, elastic material for different combinations of the EPK clay or fly ash or GGBS mixture for elevated temperature. And the first two one is the normal temperature. Bottom one is the elevated temperature. What are the values of UCS values? E values and the failure strain. And then how much is the volumetric strain? Also, we calculated over here for the lime sludge and then lime sludge fly ash. So lime sludge fly ash, when mixed with that, obviously the volumetric strain is decreased. So here, these are the failure pattern, how it looks like, for the different soils. So most of the cases, when the soil is very stiff, so the sample behaves like a brittle type of failure. And when the soil is, so that's the reason people, so if the soil feels like a brittle, then it is a problem. The failure is sudden or catastrophic. So that's the reason a lot of people are using like fiber type of material so that it can take some load or it will be more resilient. So this is the statistical analysis has been conducted using ANOVA, UCS, Young's modulus, and failure strain, and then p-value calculated is less than 0.5. At least one of the population means in different from others, and then so this is the values for the different soil sample, as I mentioned earlier, M2, M3, M4, and calculated the UCS, the failure strain, and modulus of plastic value. And then, so these are, so obviously the influence of the curing we conducted, and influence of the temperature we conducted, so all these different things. And then, so also for different combinations we conducted. And finally, from the statistical analysis, the regression model. So we use the UCS test. You are interested in UCS test, the function of fly ash, lime sludge, unit weight, dry unit weight, bulk unit weight, and the curing temperature and the curing time. Okay. So and then we develop this equation, and then from here you can use that UCS UCS strength is 0.081 times how much the percentage you use, the lime sludge, unit weight, bulk unit weight, the temperature, curing time, and the curing days. So you can use this equation to calculate and this using the statistical model. So now what is happening in this scanning electron microscope for studies, you see that lime sludge and fly ash. So most of the time, is over here, the fly ash, this is the original sample, the fly ash particles, the pockets of the voids. There are lime sludge, looks like this. When you added the mixture, so like this one, you see the EPK 5% fly ash and 5% lime sludge. There are, the more agglomeration takes place, the population takes place, and then there is less voids inside the stabilized soil. That's why the strength is increased. So we need to calculate that how much is the silica alumina ratio, silica alumina silica calcium ratio, and the sodium. So all these things you need to calculate. But again, this is EDAX. From there, you can find out what are the different chemical composition. But this is not going to, this will give you an idea. But only thing is how many minerals, how many chemicals are there. So they combine it to make it 100%. So that will not give you a quantitative one, but this will give you just qualitative chemical compositions. So these are different combinations of what is happening over here. So it's much more condensed for the geopolymer sample from these microstructures. Okay, so and then that's the reason the strength is increased. So so again, these are some of the things as I mentioned. So obviously we need to find out what are the mineral forms. So either sodium aluminate silicate hydrate or calcium aluminate silicate hydrates, all these different mineral forms. And then also that most of the time is 23 degrees Celsius, 70 degrees Celsius is much better compared to the 25, 23 degrees Celsius or room temperature. So these are again some of the pictures, micrograph of fly ash versus lime sludge. And you see for EPK clay, only 28 days, nothing. So there's a lot of voids, but with this different type of stabilizer, you can see that the reaction is better, less void, samples are more condensed because of these different mineral forms and because of the geopolymer. So in the sustainability index, I'm just going to tell that these are different index we calculated finally using this greenhouse gas, then an inventory of the carbon and energy database. We use that, and then we calculated all these different embodied energy for the lime, fly ash, and GGBS. And then we calculated that the different, I'm just going to go here, the final index, sustainability index. So we'll be getting a graph like this, and the radar chart. So most of the time, you see the original one, the method A is using lime. So this dotted one. Method B, the green one, uses 15% fly ash and 15% lime sludge. Method C uses 15% fly ash and 15% GGBS. So the more area means you are using more energy. So basically here in this case, method B, that is fly ash, 15% and fly ash and 15% lime sludge is much more sustainable for this case. Okay. So again, you need to calculate all this weighted index and stuff. We can use that from the different data from the, as I mentioned, the sources, and you can calculate all these different index, the resource consumption, environmental impact, and socio-economic impact. And finally, you got this graph like this. And then from there, you have an idea what type of stabilizer is most suitable from the sustainability point of view. And then from here, conclusion from the study is basically the lime, fly ash, and lime sludge geopolymer is having more successful use to improve the geotechnical properties. There is no record of using fly ash geopolymer-based geopolymers. So this is, people have not done this earlier. And then the failure pattern of untreated is bulky nature, but when you use that, the behavior is more stiff. And then we have seen that the scanning electron microscope, that the curing of GGBS stabilization samples under both 23° and 27° shown positive results. To higher the temperature, the strength is more. And also we did some tests like a 35°, even we checked substantial increase in the strength. And again, as I mentioned, the sustainability index point of view, that lower sustainability index indicates the more sustainable alternatives, as I mentioned from this data chart area. And then also we use that the ANOVA for the statistical analysis, the Young modulus, bulk density, and failure strain. And the correlation was R-square value is 0.7, is quite good. And then you can use that equation for to estimate that UCS value. We try to estimate the UCS value from there. Okay. And obviously, we have not done the studies only OPC. So obviously, if you use that OPC, then you can really compare how much is the strength for fly ash and lime sludge or fly ash to GGBS and compared to the OPC or lime. Okay. So again, the sustainability index, as if we are used that here we use that lime as a reference when you calculate the sustainability index. So we calculate how much is the energy required in compared to the lime stabilized soil, and then when you use that fly ash plus lime fly ash plus GGBS. So I think that is the one I just want to tell quickly. That is the one basically, as I mentioned, the geopolymer stabilized soil. So this one is durability. I'm just talking about a little bit of durability. So here, so durability also, this is one of my graduate students' work. So he studied a lot of studies. So this paper is going to publish in Transportation Geotechnique. So here he used the fly ash and GGBS also for geopolymer for high plastic clay. So basically, I'm not going to talk about that basically. So why use geopolymer? The idea is, so we are not using conventional material like a cement or lime. That production itself generates a lot of CO2. So geopolymer is eco-friendly. And then here in these studies, what you did, like most of the cases, the geopolymer, we use the mixing process, the wet method. So over here, a traditional geopolymer, so we use fly ash and geopolymer soil sample. And then we use that alkali precursor, sodium hydroxide and sodium silicate solution. And when you add water in sodium hydroxide, it generates a lot of heats. And then sodium silicate, you mix this solution, keep it overnight. And the next day you add with the, in the mix with the fly ash and GGBS and soil together. Okay. And then the geopolymer is going to form basically when you keep it either natural or maybe, inside the oven for 70 degrees Celsius. So this is traditional method. So we tried, because when you add water into the NaOH, it generates a lot of heat, so why not to use that heat, to without increasing the temperature of 70 degrees. So see what happens. So we use fly ash GGBS, water and sample, and we grinded that NaOH in powder form, and then we add it together, everything together, okay, and mix it and cure for normal temperature. So normal temperature, so you see just normal temperature, what is happening, okay. So we are not using elevated temperatures, and then see what is happening. So using just using the heat from NaOH, okay, when we add water into that. So here, so we use some clay. This is not the EPK clay like the previous studies we mentioned, the commercially available. This is actual clay, and then and then we use the fly ash and GGBS, and then that we mixed with different percentage. We mixed with the dry mixing approach. We mixed the wet mixing approach, compared with the wet mixing approach, and then we did that the wetting, drying, and freezing thawing durability test, and also we did that ACM test. So basically, you see, this is clay. This is a clay soil. This is the fly ash, and this is GGBS. Here, I just want to mention over here, this is also class A fly ash, obviously. So here the sodium hydroxide, we use 10 molar. So again, various studies are there. They're used from 5 molar to even 20 molar. So based on the studies, the literature, so we use the 10 molar, NaOH, and then we use the sodium silicate also. So these are the combination we used for these studies. Basically, we used pure clay. We used 5% fly ash and 5% granulated blast furnace slag, plus geopolymer. We are talking about the geopolymer is basically we are using sodium hydroxide and sodium silicate. And then the second one we tried with clay with 10% fly ash and 10% GGBS plus geopolymer. And then the third one is 15% fly ash, 15% GGBS geopolymer, and 20% fly ash, 20% GGBS and geopolymer. So different combination you use and to see what is happening. Okay. So basically, as I mentioned, the wet mixing method, and then how you compare with the wet mixing method also, what is happening with the studies. Okay. So here, these are the different tests we use. So we use, as I mentioned, that clay is not CaS, it should be C. So clay is 43% clay, 52% silt. Fly ash is mostly the silt. And then GGBS is 41% silt and 9% clay. This is the particle size distribution graph. And then the chemical composition is very important, as I mentioned earlier. The chemical composition of fly ash, GGBS, and blast furnace slags. Over here this fly ash is used over here is class C. Is the calcium is 22%. And then specific gravity of the clay is 2.65, liquid limit is 60, and plasticity index is 34. This is for experimental test for, as I mentioned, for design mix. I think I've seen this. So this is the combination for wetting drying and freezing thawing. So meaning WD0 means basically is just pure clay. It's nothing added. Freezing thawing also FT is freezing thawing 0% only for the clay. If we have 5% means WD5 means 5% fly ash, 5% GGBS and geopolymer. And then it is wetting drying is WD and FT is for freezing thawing. These are the combinations we used and the notation. And then this is the behavior, okay, of the stress strain behavior. Over here, you can see the clay is at the bottom without anything. And then this is clay with, so 20% fly ash and 20% GGBS is the highest one. Okay. Then this is for the 28-day strength, stress strain behavior. So geopolymer stabilized clay soil at 28-day strength again is the clay. And then you see here like a standard modified Proctor test type of behavior. You see the more stiffness, the modulus plasticity is also increases. And then this is C, and then this is the one you see here 20% fly ash and 20% GGBS for 28 days. This is the UCS strength again for 7 days and 28 days. So 7 days and 28 days, you see not much of difference, in the strength, 7 days and 28 days. You see here some of the cases, some combination is almost the same value. It's not much of difference, Here in these combinations, 15% fly ash, 15% a little bit more, 20% is a little bit more, but not much difference. Okay. UCS strength over here. So this is for different combinations. You can see the values of also here, and then the modulus of plasticity, how the modulus of plasticity is changing for 28 days. So 7 days and 28 days. So this is first column is the 7 days, is 28 days. This one is 7 days and 28 days, not much difference. This is also not much difference, as I mentioned earlier. And then also how the UCS E value is, elastic modulus is also going to change with different combinations. So C is the pure clay, and this is fly ash plus GGBS, 5%, 10%, 15%, and 20% fly ash, 20% GGBS. So then this is the failure pattern, how it looks like. So most of the cases, if it is pure stabilized soils, and stabilized also, we can find out, like in most of the cases, it is, if it is more stiffer, it's more brittle failure type. So now for this wetting and drying test, so you see the untreated samples, it dissolves immediately. Okay, these are the samples you prepared, and then I'm not going to explain how to do that. So most of the time, there is a standard procedure, ASTM. So you need to prepare the sample, and then you need to insert into the water, and then keep it for certain time, and then take out. And then when the sample is there, it's a dry it, and then you brush it using a wire brush, and then see how much is the loss. So from there, you can find out how much is the loss, how much is the volume change, all these things you can calculate from there. And then same thing you do when you keep it in the freezer also, the freeze, and then you take out, and then also do how much is the loss or volume change and stuff. So here, untreated sample collapses immediately, it's like this. And these are the samples for the wetting, drying, and then after one cycle, it's almost intact. This is after 2 cycle. So here for we use 2 identical samples for each test, and this is sample 2 after 3 cycles. This is only 1 sample is remaining, so other is not very good. Sample 2 is after 4 cycle. Same thing for this is 5%. This is 5% fly ash, right? So WD is basically 5% fly ash and 5% GGBS, and with geopolymer. So this one is WD10, means in the notation you mentioned 5% 10% fly ash, 10% GGBS, and geopolymer. So this is, you see, with the geopolymer, so 1 cycle is survived, 4 cycle, all these survived, 7 cycle, and 12 cycle, only 2 samples are survived over here. So basically this is a durability study. So you see it's much more durable when you use geopolymer. So this is again some of the pictures after 1 cycle, 4 cycle, again after 1 cycle, 4 cycle, after 8 cycles. So what is happening basically for the sample over here? And then if you calculate how much is the mass loss, so with wetting, drying, if the 5% is mass loss is much higher compared to the 20% WD over here, So 20% and 50% is almost the same over here, So 20%. So is, we need to check. So which one is the head loss is the mass loss is. So mass loss is more is not good, right? So mass loss is less is better. So so continuous increase in the mass loss observed in the cycle progress, and primary due to the extinction or leaching of the particles during wetting phase. So basically how the sample is, if it is not contact in a matrix forms, it's going to leach out. So volume change, the volume loss also you can find out from the same sample for the wetting drying test. And then the bulk unit weight is not much change in the bulk unit weight. Okay. And then same thing also, same soil combinations, but for freezing and freezing time thawing test. So freezing thaw effect for the first cycle. So, and then these are the different cycles for freezing thawing. You see the first cycles after first cycle. So this is the effect on freeze thaw without any stabilizer, without anything. This is the situation. The first cycle itself, this is already cracked or broken. Maybe at the joint it came out. But for freezing thawing for 5% fly ash, 5% GGBS, this is after 1 cycle. After freezing thawing of 2 cycles, 2 cycles, after 3 cycles. So this is happening, what is happening freezing thawing. And then also wetting, drying, and freezing thawing. So this is the situations over here. And this is not the wetting drying. This should be freezing thawing. This is also freezing thawing, but 10%. Okay, this is 5%. This is 10%. This should be freezing thawing, not wetting drying. Okay? And the mass loss over here is 5% is more mass loss, and then 10%, and then 15 and 20% is also the same. Okay? volume change behavior or volume loss is also, you can see from this graph. Bulk unit weight also decreases progressively with each cycle because sometimes, multiple cracks, it store a lot of water into that. So that's the reason, the unit weight is increased. So over here, this is the, as I mentioned, this is the dye mixing method used. So we used wet mixing method also earlier studies. So we compared with that dry mixing and wet mixing. What is the difference? So obviously, the wet mixing is the strength is much more for the same combinations. The dry mixing is 7 days and 14 days. MPa is much less every time. For the dry mixing is every time the strength is much less compared to the wet mixing. Okay? Because the wet mixing we used only the heat from the NaOH, right? So we have not used. So maybe the mixing is not proper. In wet mixing we use that sodium hydroxide and sodium silicate in solution, and then mixed with the clay and the stabilizer. The mixing is much more proper. Maybe here sodium hydroxide and sodium silicate is not reacted or not mixed properly with the soil. That's the reason maybe in a dry mixing method is the strength is much lower for exact same combinations of the soils. Although this is we compared with EPK clay, this is the normal clay. Okay, but just for the comparison. And then again, this is the particles, the scanning electron microscope of the pure clay. This is GGBS, this is fly ash particles, and then with 28 days, the 10% fly ash, 10% GGBS, how it looks like is much more condensed structures, with less voids. And then because of this formation of either calcium silicate hydrate or calcium silicate aluminum hydrate. And again, this is 15% fly ash and 15% GGBS. So even, you see how the microstructure looks like. So much more dense structure, more dense structures. This one is that 20% fly ash and 20% again, you can see it's much more dense structures compared to the untreated sample. And then finally, what you have noticed that over here, dry mixing method proves effective. 25% fly ash and GGBS geopolymer exceed the criteria. If you consider the ASTM criteria for UCS strength, that over 0.8 megapascal, then it can be used for soil stabilizer purpose. GGBS and fly ash geopolymer increases UCS strength for both 7 days and 28 days. So 28 days peak is 834 for 7 days and 967 for 28 days. So it increased like a 267 to 190% compared to the control test when you're not using anything. So 7 days and 28 days is not much of difference. The 10, 15, and 20% mix is so excellent resilience, surviving all 12 wetting and drying cycles. And then mass loss and volume loss decreased with the higher geopolymer content. And then with 20%, so the least loss. So 20% mix is the best combination. And the strength increase, as I mentioned, is 267% increase for 7 days and 190% increase for 28 days. And then for all mixes, mass and volume loss were higher than the initial cycles, followed by considerable decrease in the subsequent cycles. So geopolymers sample are effectively affected by freeze thaw. So freeze thaw, so no. I mean, for all the combinations, no samples survived after 12 cycles. Whereas the for wetting drying, samples survived. So freezing thaw is more. It seems like more harsh. Mass loss and the volume increase with each freeze loss cycle due to bulking. while bulking density steadily decreased. And SEM images, is a thick and compact microstructure because of this formation of calcium aluminate silicate hydrate or sodium aluminate silicate hydrate gel. And then that's the reason, the durability is increased. And so all this, as I mentioned, like these durability studies for anything. I mean, this is just one example I mentioned over here. And if you want to read more details, so these are the paper. These are the results I've taken from this paper, of my paper. So if you want, I can send this paper for further studies. So basically, this is basically the geopolymer. I talk about geopolymer. I talked about geopolymer, how when you mix in dry situation, that is not common. Most of the time you use in wet form. So what is going to happen? And we discussed about like a ambient temperature, and then also we discussed about the curing temperatures. What is going to happen to the strand? Okay? And then so as I mentioned, so you know how much time I have now? Anyone can tell me how much time we have?
Maybe next 15 minutes, 10 to 15 minutes.
Okay. All right. So now the last topic is basically I'm going to talk about, but again, I'm not going to go and discuss in detail. So basically the ground freezing and ground heating. So mostly the ground freezing is basically is developed in 19th century. So basically what you need to do if the water table is too high, water content is there, so you just freeze the whole ground, okay, and then do the excavation and construct something on that type of soil. And there again, is not a cheap method, so you can use that. When you cannot use any other method, so in that situation you need to use this. Okay. So as I mentioned, this is started in Germany. People are using it frequently here in US. I know there are some projects in New York and California also. And I just want to mention over here that in ASCE Geo Institute site, if you can go ASCE Geo Institute site, and there is a geotech tool, there you can find out a lot of information on these different ground improvement methods. And then I was involved in this ground freezing method with Joe Sopko from Ground Freezing. He's the director for that company. So we had a small project from ASC and we did that. So please look into that. That ground freezing we created. There a lot of information is there, different case studies, a lot of pictures. And then also mostly application for the tunnel applications, and also that the construction of drill shaft. Okay, so there are two main topics there, and then also different case studies from different countries. So this is a very nice source information of this ground freezing, and we did that last year. So hopefully everyone can see that. You'll find out more information about that. The ground freezing, as I mentioned, so it can, generally is a drilling technology, freezing and drilling technology in advance, more applicable for the civil construction. So it started in 1950. Extremely difficult of the soil, can be remediated with great success. So obviously, again, you can do it like a foundation shoring. You can do the coffer dam. You can do underpinning work. You can do temporary access road using soil freezing. Is more common. So we can go up to even 2,000 deep, 2,000 feet deep for the construction using freezing method. And again, it is expensive. It's not easy. So now how to freeze the ground? There are the principle of ground freezing is ground freezing process in which the in situ pore water is converted into ice. Okay, like in like the cement in concrete, right? Ice bonds soil particles together, and then imparting the strength and impermeability of the frozen soil. So, frozen soil, the ground freezing is based on the withdrawal of the heat from the soil. So you just really remove the heat and then and freeze the ground. So basically, what you need to do, you need to pipeline system like a dewatering system, you use that the pumping the water out. Say a pipeline system, you just freeze the ground using either using brine solution or using nitrogen, liquid nitrogen. So you use that inner pipe, the pipe into the ground, and then either brine solution. It can be closed and open source, and then freeze the ground and then do your construction. So over here, brine freezing, you see the freezing ground over here. So you use a cooler, and then you just one pipe, it will go that calcium chloride solutions, and then the lowest temperature can be achieved by minus 55 degrees Celsius. So it can be, so this is how you freeze the soil. And then this is calcium chloride, how the circulating the brine. You see over here the same supply. There's this closed system, and then you freezing the whole soil over here in this ground. Again, I'm not going to go into the interfreezing plant. Consists of the number of freezing unit, how many number of freezing units is required. The same thing like dewatering technique. Several additional components like a low voltage switchgear, tank of the brine solutions, how many, and then recooling machine. So again, I just want to show you some pictures and some of the graphs requires freezing time. So this will give you an idea how many spacing on the pipe or required freezing time is required. So depending on the water content and also freezing time versus the distance from the freezing pipe. So again, you have a freezing pipe like an influence zone, right? The same thing also, how much is the influence zone will be when you freeze that ground. So this will give you an idea that, and also how much is the the freezing pipe spacing, right? So application is, it can be temporary underpinning structures. It can be ground support to seepage control during tunneling. Large open excavation, retaining structures, tunneling through the full space granular soil, sinking and lining of mine shafts. So a few things when there is a leakage of water, is there temporary cut-off wall, all these things where you need to, there's a problem with the water, you freeze the ground and then do, or when the construction is, even machinery cannot go, freeze the ground and then the machine can go and then do your construction. So as I mentioned, it can be temporary method, it can be excavation, support for the excavation, it can be tunneling, it can be underpinning our existing structures or environmental applications. So again, these are some of the pictures you see for the tunnel. It can be for the retaining structures, for the open structures. People don't use it mostly for the shaft or retaining wall. This is how we do, like it's frozen the whole soil, the first one, and then you see just cut it, the wall support and then cut it. Like in tunnel construction, what you do. Only thing is, I'm just going to go in detail. I'm not going to go. So here, you need to understand if you want to read more details, like a frozen soil, that the phase diagrams here, the gas, here is the water unfrozen and water is not frozen. And then water is forming ice, okay? And then the solid. So these are the few things you need to know while designing this, that how much is the unit weight or density will be. Again, the specific gravity, gamma W by 1 plus E plus here, it is a little bit different than conventional one, okay? And then if you use liquid nitrogen, so this is how you do, like a supply the liquid nitrogen and then come out, and then the whole soil is going to freeze, okay? And it can go up to minus 196 degrees Celsius when you're using liquid nitrogen compared to the calcium chloride or brine solution. So I'm not going to go in detail. So here, this is some of the pictures. Again, ground freezing a technique extremely used for ground control, groundwater control, and excavation support for the underground construction. So underground construction, you just freeze the whole ground, so it's not going to collapse. So that's the idea. So again, as I mentioned, so you can find out several pictures from geotech tools. Okay. Similar principles, I'm not going to go in detail over here. So this is how it looks like. You see there is freezing pipe over here, the header and riser types, and then freeze the whole soil, and then do the excavation, at the middle. Okay. So that's how it's easy to construct. But again, this is expensive. So you have to keep this running while doing the excavation, until you put a cover material while the excavation is done. Freezing process, there are indirect process or direct process. I'm going to go in detail over here. And then, so this is some of the freezing methods. I'm just going to go here. Mostly, as I mentioned, this is SAP applications and the tunnel applications. Okay, and over here, how it looks like. But again, you can see different several pictures in that in geotech tools. Large open excavation, you see here all these freezing pipes, and then whole thing is frozen, and then you excavate and do the open excavation. So for designing this and for quality control, again, you can use the geotech tool. We did that and uploaded last year, so you can find out all the materials, quality control, how to design, what are the different software you can use for that. Mostly people use Plaxis and other softwares. And then also this is like what is happening, the SAP freeze wall formation. So what is going to happen? What is unfrozen soil, the frozen soil, how the plasticity or elasticity is going to change. So you can find out from there. So I'm not going to talk about that more theoretical stuff. But again, as I mentioned, so we can find out all the informations in the geotech tools. Okay, so as I mentioned, the process making water bearing strata temporarily impermeable. Freezing is normally used to provide structural underpinning, temporary support, and then also no extra material is needed. So because we are not doing anything. So basically, you're not adding chemicals, it's just we just freeze that water. That's all. So nothing is required. No extra material. And then normally used to provide structure. So this is different application as I mentioned. I just mention that it can be used for any soil, rock formation, regardless of structures, grain size or permeability. Best suited for soft ground rather than rocks. Obviously, the water should be there, right? So you need to freeze the water. Freezing water may be used for any size, safe and depth excavation. The same cooling plan can be used for the job to job. So you can use that, move that like you can use for a boring machine or rig to transport the same thing, same freezing system you can use for different site. Okay? I think principal freezing, I'm not going to go in detail over here. So basically, this is another freezing technique. As I mentioned, the Joe Sopko is the one. He's the director for that, the ground freezing company, and we developed that ASC geotech tools. There are a lot of informations are there, and so this is you see the different pipelines over here. So basically, the header and riser, like the same thing we mentioned with the dewatering technique. So only thing is here in the pipeline, we need to supply either liquid nitrogen or calcium chloride. That's all. Okay. So I think that's all, for this ground freezing. I just went over quickly for the sake of time. So basically, the ground freezing tool, as I mentioned, so in AC, go to the AC site, Geo Institute, Geotech tool. This is the one last year we developed this, all these techniques and everything. Specifically, Joe Sopko is the one is expert in this ground freezing. And there are a lot of project basically in California and New York where they use this ground freezing technique, especially for the tunnel and the drill shaft foundation. Okay. So this ground freezing and ground heating is when the soil is generally the very soft soil, just heat it and then just remove the water. But also the properties is also going to change in that situation. So we are not I think in the first slides in ground improvement we mentioned that, but not in detail. Okay. All right. I mean this one is again you need to read that the geotech tools. There you can find a lot of information. My only thing is here that the different mechanism, how to design that instead of three-phase system like a soil, air, water, and air. So here the ice is coming into pictures. water, some portion will be ice, some like unsaturated soil mechanics, right? Some portion of the voids are filled with air, some portion is water. Here, some portion of the field is air and some portion is already ice. Okay. As I mentioned, if you need anything from this geopolymer or durability, we are working on that still. This is a lot of, I know there's in IITs or NITs, a lot of people are doing research on that area. The practical thing is, I know that geopolymer, we need high temperature, but in Australia, people already use that geopolymer. There is a method to use, and then in US, not many people are using here in practically, but I think I'm sure people will be using this geopolymer. It's much more sustainable. The strength is much more compared to the convention. All right. Any questions or anything? I can, if anyone needs that, the paper I mentioned, the 4 papers where from I presented the durability and geopolymer, I can send that paper to everyone. If
There are a couple of questions on charts.
Which
Meeting
one?
chart. Yes, sir. Meeting chart. Can you read out?
Sir, there is some questions in meeting chat. You can see, sir.
I can see that only earlier chart. So where is the chart?
Sir, meeting chat in like near the participant.
Yeah, I click that. So chat preview. The earlier one I can see. I can see the last chat here. Yes, sir. Thank you. That's all. The GPS one. What about the other chart?
No, this is the only one, sir. What is the durability aspect of using GGBS?
Oh, okay. So that's the last one. Last time I mentioned that GGBS is, again, we have seen that the durability, correct? Sometimes, we need to be careful while with the freezing thawing or maybe the wetting drying, right? So the current study we have seen that if you're using GGBS, so we need to have some activator, either a little bit of cement or lime, or if you are using GGBS with that geopolymer, obviously that's the sodium hydroxide, sodium silicate, it's much better, as you have seen the freezing. But freezing thawing is the worst. You have seen that the earlier studies, and then the way it can survive. So you need to do different right? How many serval? Right? So then it is much more durable, right? Index. So mostly you do the freezing thawing cycle. Whatever the sample survive, if it is in good shape, and then again. So then you can find out how much is the durability index. So you can find. And also a lot of ability for the concrete. I know that the acid test and other tests, you can do this for the soil also, soil stabilized, but we have not done that. So I'm sure people can do that.
Sir, one more question. Can you please have a look regarding lime stabilization for expensive clay which have a higher plasticity index?
Okay, that's why we mentioned already, correct? So initially that the density will go down, but at the same time, with time, with the curing period, it is going to they increase the strength, right? So in expensive clay or maybe is more, again, what type of expensive clay, correct? If you're using kaolinite, it's different. If you're using monzonite, it'll be different, right? Again, what type of reaction takes place. We need to check that reaction, and also even we need to see that the diffuse double layer stuff, how, and the zeta potential, all these things you need to check to study really what is happening in the microstructure level.
Okay. Thanks.
All right.
That's fine, sir. I think if everything is okay, we can close the session, sir, because the tutorial we have from, I think it's not what is time now, 10. Yeah, 10. Actually, we have a tutorial, but we will try to circulate the questions So they will solve it themselves. If they have any doubts, they will.
Okay. Okay.
Yes, sir. We will
So
do it.
I think in the schedule, just I have the only one tutorial session, correct?
Sorry, sir.
I think only one tutorial session I have. This one,
Yesterday that was
yeah,
over.
yeah, that's one I did it today. But I'm not happy at all. I mean, the way it was going. So, but anyway, what to do?
Yes, sir. So tomorrow you have a 2 hours lecture, sir, from 6:30 to 9:15. 2 hours
Okay.
minutes.
So basically the grouting and soil nailing and anchoring, and then the soft soil stabilization and MSC. There are so many topics, but time is short. So that's why I'm just showing click, just showing the slide. That's all, nothing. I mean, just filling out. I don't know what to do. I mean, either you need to just one topic, go in detail, and then otherwise, if you want to cover everything, just go quickly.
No
We cannot just.
issue, sir. Tomorrow we have a 2 hours.
So if you need all these, like the slides, whatever, although it is recorded, but I don't know if you need all the slides. Original, I put it in one drive, so anyone can access that if someone need it. Just only the slides. So that site can be used for teaching or anything. I mean, this is my slides I prepared, but can be used for anyone if you want to use it. Also, I collected from the several sources. And also from my research. I mean, it's an ongoing process, right?
Yeah, exactly.
So, all right. If someone get benefit or someone is, because I compile everything together, so it'll be easy.
Yes, sir.
All right. So anyway, so I just, as I'm doing it, like I just go quickly, just touching all this cover all the material. We'll be doing this mechanically stabilized alternating wall, and the last one, and then day is 19th is just only the sustainability aspect, right?
Sustainability.
Technical engines. I'll talk more. So that is the one I talked a little bit of the sustainability index. Leave it today. I will talk more about that, the greenhouse gas and other things on that day, and then how to use it for different industrial material, waste material. So basically, that is much more sustainable. All right.
Right, sir. Thank you. Thank you very much, sir.
Thank you so much.
Yeah, no problems.
Okay. Bye.
Okay, sir. Bye. Thank you. Okay.